Here, talking about how we transport gases there. All right, so we carry both oxygen and carbon dioxide in the blood, plasma. Plasma is, in terms of definitions, blood plasma is the fluid component of blood that does not include any cells. Okay, so plasma is water, lots of water, and it's proteins, and it's all the electrolytes, sodium, chloride, etc. Okay, but it's none of the cells. So no white blood cells, red blood cells, platelets, any of that. Okay, so when we talk about plasma, we're talking about an aqueous solution with some ions and some proteins. Okay? And as it turns out, we've talked about this before, that oxygen has a pretty low solubility, right? So in our normal alveolar oxygen content of 100 millimeters of mercury and PO2 of 100, we actually can carry very little oxygen. Okay, so about 3 milliliters of oxygen, okay, 3 milliliters of gas in 1 liter. Okay, so a tiny little bit of oxygen goes into 1 liter of blood plasma. Okay. But we have a way of enhancing that, and that's with red blood cells. Hemoglobin is the major protein inside the cell, so it's an intracellular protein. And hemoglobin makes up about 1/3 of all of the proteins inside of our red blood cells. Okay. This is not a number you need to know, but there's oxygen binding capacity that we can measure, right? So 1.34 milliliters per gram of hemoglobin. Okay. So in about 2 grams of hemoglobin, we can carry the same amount that we can dissolve in a liter of plasma. So there's quite a lot of oxygen carrying capacity. Okay, normal hemoglobin level up there. Again, don't worry about this number, but as you go on to your clinical lives, you'll care about this because hemoglobin can change, right? And if you don't have enough hemoglobin, what do you have? Anemia, right? You have decreased capacity to carry oxygen in the blood if you've got insufficient amounts of hemoglobin. Okay, so you can see that we have very conveniently, maybe a little too conveniently, a total of 200 milliliters per liter. Okay, it's pretty close, but it's an estimate. 200 milliliters of oxygen now we can carry in a liter. Okay, so we have substantially increased. I think it's about 65 times as much oxygen that we can get in our, if you do the math here. Somebody want to do that? 197 divided by 3. I think about 65%, or 65 times. Yeah? No? Close enough. That's about 65 times the amount of oxygen found on hemoglobin. Okay? All right, so good for us. Aren't we great? We've got this hemoglobin molecule. What's it look like? There are 4 peptide chains, each with an inorganic, each with an organic ring structure called heme, right? So this is what heme looks like. And at the center is the inorganic ion, okay, Fe plus 2. And this Fe plus 2, this iron, is where oxygen is able to bind, okay? So there's one of these ions per heme molecule, 1 heme molecule per peptide chains, 4 peptide chains. So we have the ability to carry 4 oxygen molecules, okay, in 1 hemoglobin. Okay. So there are things that can affect this. So we've got things like nitrates and sulfonamides and these sorts of chemical compounds that can affect the state of iron so that it's Fe plus 3 plus instead of 2, right? In which case it's no longer able to bind oxygen. So the hemoglobin concentration doesn't tell you everything. There are circumstances where you might have normal hemoglobin, but are unable to bind oxygen properly. Okay. And that hemoglobin with Fe3 plus is referred to as methemoglobin. Most of us, let's say all of us, are not fetuses, and fetuses have a unique type of hemoglobin, okay, compared to those of us who have been born. We all have in common the fact that hemoglobin has 4 chains, but the chain composition is a little bit different. So we have 2 alphas and 2 betas in what we call adult hemoglobin. Okay, you see that up there. And there's a variant of this. There's 2 delta hemoglobins. We're going to have 2 alphas and 2 deltas instead of betas. This is found in a very small percentage of all of our red blood cells. Okay, so as adults, or probably more accurately postnatal individuals, right? We have so even children, even though it says adults, we all have alpha and beta as the primary mix, but there's a little bit of delta as well. Okay, there's a third type of chain, which is fetal hemoglobin. Okay, in which case the betas are replaced with gammas. Okay, now what do you know about fetal hemoglobin? What makes it unique besides the fact that it's found in fetuses? What are the characteristics of
Does it have a higher oxygen carrying capacity?
not a higher capacity for oxygen. It's a slightly different term. Yeah.
Higher oxygen binding
Affinity, yeah. So when we talk about affinity, this is how strong the attraction between hemoglobin and oxygen. And so fetal hemoglobin, you put those 2 gamma chains in there instead of the beta, now the characteristics are a little bit different. It grabs a hold of oxygen more strongly. Why would that be important if you're, say, a fetus? Yeah?
You have to be able to steal the oxygen from the mother's blood supply.
Yeah. Well, any good fetus has to steal to get by. You guys have this too. You have fetal hemoglobin. You have the gene for it because you once used it, but we no longer express that gene. The fetus definitely needs this ability to more strongly attract oxygen. And so what will happen is that the fetal hemoglobin will essentially pull oxygen away from the maternal blood and then to serve its own needs. Okay. All right, that's a good thing. Okay, so we're going to talk a little bit about how how oxygen moves through from alveolus into the red blood cells. But I want to make a point which is sort of obvious when you look at it, but we often forget it, and that is that the blood plasma stands between the oxygen in the air and the oxygen that gets bound to hemoglobin. Okay, so every molecule that will ever bind, every molecule of oxygen that's going to ever bind hemoglobin has to first be present in the blood plasma. Okay, so that oxygen molecule up there in the alveolus can't jump directly to the red blood cell. Okay, everything gets mediated through the plasma. Okay, and the same is true of the opposite process where oxygen goes from our red blood cells to the cells of our bodies that are using oxygen. It's got to go through the plasma, okay, on its way to the interstitial fluid, and from there to the cell. So keep in mind there's a path for this. It's not direct all the time, even though we can kind of talk about, okay, oxygen is going to go from your red blood cells to your cells and systemic capillaries, but really what we mean by that is it's going to pass successively through these various fluids. Okay, so in order to talk about what's going on here with hemoglobin, we get to talk about everybody's favorite, the oxygen hemoglobin saturation curve. Okay, now I know some of you have had this in other courses, so good for you. Not everyone has, so we'll have to go through it. Okay, there's a little bit of chemistry here, and I want to point out this little equation at the bottom. we've got oxygen. You all know that, O2. This hemoglobin with an H in front of it is deoxyhemoglobin. Okay, so when there's not any oxygen bound to it, we refer to it as deoxyhemoglobin. And you probably know that H stands for hydrogen, right? So what happens is oxygen, when it binds to that Fe+2 as part of hemoglobin, we're going to get oxyhemoglobin, okay, and then a hydrogen ion. What do my arrows tell you? Yeah, this is an equilibrium reaction, like many chemical reactions, and that is, it's reversible. It can either go to the left, meaning we are dissociating oxyhemoglobin into oxygen and deoxyhemoglobin, or we can combine those and the equation shifts to the right or moves to the right, in which case we have oxyhemoglobin and H+. Okay? So, real basic chemistry here, what would influence this reaction to move, let's say, towards right, towards producing oxyhemoglobin? How could you influence this reaction to go that way? Yeah.
You have a lot of O2.
Yeah, if you had a lot of O2, right? So if we increase O2, told you it's basic, you know this, right? Right? You increase O2, you increase the reactants here, right? We're going to drive this equation towards the right. Okay? Make sense? Does this seem like a familiar concept? Please, somebody stop me. What if we increase hydrogen? What's going to happen? Yeah, we're going to have the opposite. We're going to drive the equation towards the opposite direction. Okay. So what happens here is that we have our little equation here in an equilibrium of sorts. There's a ratio of oxygen and hemoglobin to oxyhemoglobin and hydrogen. And if we elevate or lower any of the components here, the equation shifts to reestablish equilibrium. Okay? So we'll see that what happens is we are going to initially drive this equation to the right in order to load oxygen onto hemoglobin. And then later in other parts of the body, we're going to unload the oxygen. In order to do that, we're going to lower the oxygen on the left, right, and pull that equation over to the left. Okay, so this equation runs in both directions, and it's by increasing or decreasing products and reactants that we can shift this equation. Okay. What do we call that? It's the law of mass action. Does that sound familiar to you? No? Don't worry about that. We can call it something else if you like. Okay. All right, so let's take oxygen loading. All right, we've got oxygen in our alveolus. Okay. With a PO2 of 100, 104. Okay, and what's going to happen here, big picture, is that we're going to be moving oxygen from the alveolus into the blood plasma, right? And from the blood plasma onto the hemoglobin, right? So we're going to move that oxygen, pump it over to the hemoglobin, right? And it's going to load the hemoglobin molecules up with oxygen. Okay. So conceptually, I want you to think about it like this, and here's some numbers you do need to know. When we talk about oxygen, we need to know that we have a standard PO2 in the alveoli of 100. Call it 104 if you want. Let's use 104. If you put 100 on the test, you won't get it wrong. That's good. Perfectly fine. Okay. The plasma O2 that is entering pulmonary capillaries. This is blood that has come from the venous circulation of the body, right? And is now going towards the pulmonary capillaries. Has a PO2 of about 40 milliliters per mercury. hemoglobin in this state where we have already used some of the oxygen, hemoglobin is down to about 75%. That is, there's room for another 25%. Okay? We've consumed 25% of the binding capacity. Okay? So this is blood arriving at pulmonary capillaries. Okay? In the end, what do we want to happen to the PO2 of plasma? Do we want it to go up or down? It's going to go up, right? As oxygen moves in. What about our hemoglobin saturation? What do we want to happen? We want it to go up. Okay. So we're moving oxygen from the alveoli into the plasma and onto the hemoglobin. Okay. All right. So how does this work? Well, as you can see here, the little animation, we've got oxygen coming in from the alveoli, reaching equilibrium. Right. So it's basically moving from the alveoli to the blood plasma. And as the blood plasma levels rise, we get a corresponding rise in hemoglobin, right? Because oxygen is moving from the plasma onto the hemoglobin molecules, okay? So the hemoglobin goes up, right? Simple enough. All right. And as this process continues, plasma O2 is going to go up more. How far can it go up?
98.
What's the highest it could go in this scenario? 104. Okay. It's at that point where we have reached equilibrium. Okay. Not to say we have the same concentrations of oxygen in the alveoli and the plasma, but we're at equilibrium. Remember the whole weirdness of the PO2? Yeah, okay. All right, so plasma comes up. What's going to happen to hemoglobin saturation? It's going to go all the way up. Okay, so it goes up to 100%. What if we increase our alveolar PO2? Let's say we went up to 200. What's going to happen to the plasma O2? It's going to go up to 200. What's going to happen to hemoglobin saturation? Nothing. Okay. So at normal values, in our normal atmosphere with a normal alveolar ventilation rate, we get 104 for our PO2 of alveoli. We get the same for the blood plasma, and we get pretty close to 100% saturation. Okay. So we don't need any more. But we could, in theory, raise that plasma O2 very high. And it's just not going to have a huge effect on hemoglobin. Okay. Any questions about what's happening here? Yeah.
So if you were to increase the PO2, but like not increase, well, like his hemoglobin can't increase anymore, is there like a, do you reach a point where there's like too much oxygen?
So you can't have too much oxygen. You're not going to have too much on your hemoglobin because you can only carry so much. But there is no theoretical maximum to the PO2 in the plasma. So you could go up to 1,000 if you wanted to. Okay. There's downsides though. Oxygen generates free radicals, and that's definitely harmful to our tissues. So, in fact, it's the generation of free radicals that is part of the reason that our systemic arterioles constrict when oxygen levels get high. They'll sort of protect the cells downstream. Okay.
What about the plasma O2 capacity that you talked about? Is that never gonna even approach that?
So when I talked about the capacity being 3 milliliters, that is under standard conditions. Okay, so that's this PO2 of plasma PO2 of 104 represents about 3 milliliters per liter of oxygen. It could go higher, right? So we could have more than 3 milliliters per liter, but we have to do some things artificially to raise the PO2 of the alveoli. Yeah, question? Any other questions? Yeah.
So when you go to the doctor and they measure your iron levels,
Yeah.
are they incorrectly testing for anemia, or because you can have hemoglobin with iron, but it might not be able to find the oxygen
I don't know the answer to that. So you do have, I would say that it's somewhere in the 90 to 95% of your iron that's in your blood is part of hemoglobin. I don't know whether they're separating the plasma from the cells to do that, but you do have some in the plasma bound to, there's some iron transporting proteins that shuttle iron around. So I don't know what they're measuring, if it's direct hemoglobin iron, but it's a pretty good proxy, even if it's total iron.
But you could be anemic even if you have high iron because your hemoglobin couldn't pick up O2 if it was like mutation.
Yeah, there's, so the iron doesn't tell you, the iron tells you how much hemoglobin you have. And yeah, you can have situations where you're not able to carry oxygen on every hemoglobin molecule, right? That hemoglobin, for example, that I talked about, yeah. But when they if they're measuring iron, it's a pretty good proxy for how much hemoglobin you're making, and it's also a good indication that you've got sufficient numbers of red blood cells. Yeah.
Does the PO2 of the alveolar air always stay at 104 because you're constantly bringing in oxygenated blood?
Yeah,
Or would that be-
that's a good question. Conceptually, what's happening here is we say alveolar air has a PO2 of 104, right? So this is your lung, alveoli, right? And let's say you just inspired some air. You know that what's going to happen is that the PO2 is going to go up, right? When you inspire, because you're bringing in new air. But then you stop inhaling, you exhale, and air's moving out. And before you inhale again, that PO2 is coming down a little bit. And so what's happening is that this PO2 of 104 is an average over time. So it assumes an even and normal respiratory or alveolar ventilation rate. Yeah, because you would expect that the O2 levels are going to fluctuate up and down a little bit between inspiration and the next inspiration. But they don't fluctuate a lot. It's not like 104 to 200. You know, it's within a few millimeters of mercury. Yeah, but it is an average. Okay, let's take a look at systemic capillaries. What's happening here? All right, so here we've got O2, and it's moved. The oxygen in the blood plasma is moving to the interstitial fluid. Okay, and why is it doing that? Why would oxygen be moving from blood plasma to interstitial fluid? Yeah, there's partial pressure difference. Okay, we've got 40 in the interstitial fluid, typical average. Okay, and in the blood plasma, now that we've loaded it up in the pulmonary capillaries, that blood comes around to serve our systemic capillaries. Okay, and so we've got a partial pressure difference. Here we've got 98 on the blood plasma. It drops a tiny bit along the way, but we've got a pretty strong gradient here from 100 to 40. Okay. So what's going to happen as blood moves through the capillary is that your plasma value is going to come down as oxygen moves from the blood plasma over into the interstitial fluid. Okay. And as it does so, the amount of oxygen in the blood plasma being lower draws oxygen off of the hemoglobin molecule. Okay. And now our hemoglobin level has gone from 100% saturated down to, let's say, 90. Okay. And we'll go a little bit further. All right, PO2 is down to 40. At the very end of the capillary, right, the blood has been losing oxygen. Very end of the capillary, now we're down to 40. Okay. And what happens to the hemoglobin saturation is it comes down to about 75%.
So, there's O2 just in the blood plasma floating around and O2 on hemoglobin. So
Yeah.
it's not just all.
Right, so the blood has O2 in the blood plasma. It's a small fraction, but it's in the blood plasma, and there's oxygen found in hemoglobin. And it's because oxygen is leaving the plasma that the hemoglobin loses its oxygen, okay, which then goes into the plasma. Okay. Why does our blood plasma O2 come down to 40, but the interstitial fluid doesn't go up? Why doesn't the interstitial fluid O2 go up? What's happening to that oxygen? Yeah.
The cells are using it up.
Yeah, the cells are using it up, okay? So remember, we're in a state of equilibrium of sorts, that we have an equal amount of oxygen consumption by our cells as the amount that's being pulled across into our alveoli, right? And then from there, the blood is transferring oxygen from the blood plasma into our cells. Okay, so this value of 40 in the interstitial fluid doesn't really rise, okay? There's oxygen being consumed by cells at the same rate that it's being replaced by blood plasma, okay? All right, so let's take a look at this on the actual curve, but wait, a poll everywhere question. I forgot this was coming. All right, people. All right, so increasing PO2 in plasma increases oxyhemoglobin. Okay, that's absolutely right. Very few dissenters from that idea. So yeah, this is sort of key that it's the plasma levels, the changes in the plasma levels of O2 that drive changes in hemoglobins binding to oxygen. Okay, very good. One other quick one. See if you get fluid. Leading O2 to dissociate from oxyhemoglobin. Little check mark says that one's right. What about, there's a substantial number of people that picked the last one. What's missing from this, or why is this not a good answer, or not the best answer? Low 2 in the interstitial fluid causes O2 to leave oxyhemoglobin. What's wrong with that? Or what's not great about it? Yeah.
It doesn't include plasma.
Yeah, it doesn't really say what's happening with the plasma. So the plasma is the intermediate here, right? It's not simply that interstitial fluid magically reaches across to the red blood cells and causes some change, right? It's working through the plasma, and that's what answer B is getting to, right? Yeah, that the last one is not a whole lot different than C. If I ever use the word beckon, that's not the answer. All right, so let's look at the actual curve that describes some of the things that we're talking about here, but gives us a little bit more information. So just before we even jump into this curve, let's talk about what it is. We're looking at the relationship between plasma O2, PO2. Okay, so plasma PO2. Remember, plasma is where the action is, right? That's where the changes happen that precipitate other changes. So plasma PO2, and then we're looking at the percent saturation. So I've been using this term saturation before, but basically what it means is how much of the total hemoglobin is bound to oxygen. Okay, so if we have 100% saturation, that means that we have no deoxyhemoglobin left. We have only oxyhemoglobin. Okay? All right, so generally, this is not a linear relationship, right? You can see that it's kind of curvy, right? It's a little curvy, but you can see it's moving in the positive direction. Okay, so in very general terms, we could say that the more PO2 in the plasma, the more what? more PO2 in the plasma, the more saturation. Okay, saturation inverted. So as we move to the left, we're also moving up on this chart. Okay, so it's not exactly linear, but let's follow this through just to make sure we're all on the same page, right? So if we have a little equation here at the bottom, and we have 0 PO2 in the plasma, PO2 of 0, we have all we have all deoxyhemoglobin and 0% saturation. Okay? And if we go up to a PO2 of 40, like we find entering our alveolar, entering our pulmonary capillaries, we've got 75% saturation. Okay? And it's directly related to the amount of PO2 in the plasma. Okay? So the amount of oxygen bound to hemoglobin depends upon the plasma O2 value. Okay? And if we go up to the plasma O2 of 100-ish, okay, we're going to have 100% saturation. Okay? And no deoxyhemoglobin. Okay? So hemoglobin's a weird molecule, and it is changing its properties, right, the affinity to which it binds oxygen, depending upon how much oxygen is there. Okay. All right, so let's take a look. You can see here I've got the two values highlighted, representing 40, a PO2 of 40 in the plasma, and 100 or 104 on the right. Okay, so we have plasma PO2 of 40 starting at the systemic veins, right? Or let's say the very end of systemic capillaries. Okay, systemic veins runs through the right side of the heart, goes through the pulmonary arteries up until we get to where? What's next after pulmonary arteries, arterioles? Pulmonary capillaries, okay? And so pulmonary capillaries, the PO2 goes from 40 to 100, right? And so at 100, we've got blood leaving the pulmonary capillaries, comes back, pulmonary veins, left side of the heart, aorta, systemic arteries, right? Up until we get to the systemic capillaries. Okay, so it's going to fluctuate between those two PO2s. Right? And this represents sort of resting values. The PO2 of 40 is sort of the combination of all of our capillaries influencing one another, right? Totaling sort of an average of PO2 of 40. Okay? And then it goes up to 100. So it goes from 100 and moves back down, right? And moves back up. Okay? As it's going through these capillaries, right? So the capillaries are where we get the change in PO2. Now, can we go below 40? What would have to happen for us to go below a plasma PO2 of 40? What would those cells need to be doing? Consuming more oxygen. The cells have to be more active, right? So if we started exercising, for example, or whatever, body temperature goes up because we have a fever, something that causes our cells to be more metabolically active, that PO2 is going to change, right? So that can go down to, let's say, 20, right? And so now what happens is that we're using a much more substantial amount of oxygen on our hemoglobin, okay? So at rest, we use about 25% of our oxygen, and we can expand that quite a bit, which is great. Okay. But all of these changes in hemoglobin, all of the changing of hemoglobin from oxyhemoglobin to deoxyhemoglobin depend upon the plasma O2. Okay? We change the plasma O2, we'll change how much is bound to hemoglobin. Okay. We can make some changes to the curve. this curve represents sort of an average of what is normal for the hemoglobin molecule, but there are conditions in the body that change its properties. So we have something called a right shift. You can see the green line here, we sort of shifted the whole curve a little bit to the right, which means for a given PO2, let's say 40, we're gonna have less saturation. Okay? We have less oxyhemoglobin. What does that mean? What's happened to our oxygen? What's happened here? At the same PO2 of 40, how is this hemoglobin molecule acting differently than standard?
Has less affinity?
Has less affinity for oxygen, right? So there's less oxyhemoglobin and there's more free oxygen. Okay, that oxygen is free to go into the plasma and diffuse out into the interstitial fluid. Okay, so a right shift favors the process of unloading, right? And this happens in areas of the body where the temperature is elevated. Why might we have elevated temperature? Fever, okay, the whole body thing, right? We have a fever, we're consuming more oxygen because our cells are more active in a high temperature, and so this helps us to deliver that oxygen more efficiently. Okay? Or any increased metabolic activity of the cell is going to increase its temperature. Okay? What about CO2? We have more CO2 produced by our cells. That's going to favor unloading of oxygen. Okay? And CO2 always translates to elevated hydrogen as well. Okay, this is known as the Bohr effect. But essentially, it's the same principle where if we have metabolically active cells, that interstitial fluid around those cells will influence the blood plasma, which in turn influences hemoglobin. Right? So if we've got hemoglobin traveling through an area where there's lots of metabolically active cells, it'll be warmer and it'll be higher in CO2 and H+. And all those things are going to favor this rightward shift that helps to drop hemoglobin, drop oxygen from hemoglobin. Okay. So hemoglobin it has the properties we described in our blue line here as sort of standard, but under certain circumstances, it can shift, it can change its properties, right? And then it'll go right back to the way it was as it leaves the capillary. But as it's passing through the capillary, it'll take on more heat, it'll take on more CO2 and H+, and it'll help that hemoglobin molecule let go of its oxygen. Okay? There's another thing here, 2,3-DPG, which has another name, 2,3-BPG, which is really exciting. That's trivia for you. Your book uses DPG, so I'll use that. It's basically an intermediate in the